Today, let's go over creating a Bode plot for inverting and non-inverting op amps when the open loop gain varies with frequency. So what we want to do is plot out what the gains of these two circuits look like when we're using the simplest model for the open loop gain varying as a function of frequency, which is just 2 pi times the gain bandwidth, which you get off a data sheet, divided by S. So this is the simplest model, and as we'll see, it should be pretty good for lower frequencies. And yep, that is an integrator. You can get the SPICE file if you want from there. But just to orient you, the gain bandwidth is 1 meg. I set the resistances equal to each other, calculate some things that we'll go over later, and then I even check my work and plot the gain bandwidth. So let's come up with an equation for this using the signal flow diagram. You can use nodal analysis and you'll get the same answer, but if I take this circuit and say what's fed back here is a voltage division from out of the non-inverting, right, it'll make things a lot easier. So what is V out? Well, it's V in plus times the transfer function of the op amp, and then it goes straight out. The feedback is the transfer function of the op amp multiplied by beta and then subtracted, and beta is the voltage division. I have other notes on that. Well, then we just write it out. V out equals the transfer function times beta, right? That's why the transfer function is common to V in and the feedback path, and it's really just modified by beta. Then we collect our terms and we get 1 plus beta HS, and notice that's the minus sign here is the negative feedback. When we manipulate the math and collect the terms, it becomes positive. That's why negative feedback will have a positive term here, is because when we subtract and then collect terms, it becomes positive. So we're left with this, and we'll call it a different name. Instead of HSQS, which is just V out over V in, we multiply everything out. Okay, we have our model for the gain bandwidth. We multiply it through and we get 2 pi times the gain bandwidth divided by 2 S plus 2 pi, and there's a beta in there, times the gain bandwidth. Well, these might not be things that you're all familiar with, but we have a constant divided by S plus another constant. That's just a low-pass filter. The cutoff frequency is just given right here. Maybe in the past we used 1 over RC, but and these come from capacitances and resistances, but really 2 pi times beta times the gain bandwidth. Now what's the gain at DC? Set S equal to 0. We get 2 pi gain bandwidth divided by 2 pi beta gain bandwidth. We get 1 over beta. Multiply all that out and we get our non-inverting gain. And so by saying S equals 0, we're really kind of saying that this term is a lot bigger than the frequency term. Remember, quite often when we're finding an ideal op amp's transfer function, we let the open loop gain go to infinity. Well, this being bigger than that is kind of the same thing, letting the open loop gain go to infinity. So we've got back our non-inverting gain. We can see that our cutoff point is 2 pi beta gain bandwidth, and then we notice that QS is omega naught divided by beta S plus omega naught, right? Because omega, the cutoff frequency, omega naught is this. If I just divide out a beta, I can use omega naught in the numerator and the denominator. And so really, I get a low-pass function that you've seen quite often, but maybe the omega naught's bigger than you're used to, and then we get our non-inverting gain. And then you can plot. In this example, it was the gain was 2, and we just take 20 times the log of that to get our 6 dB, and we just draw it out flat until we get to omega naught, and then we just go down 20 dB per decade. We find omega naught, and we put that at minus 45. 10 times omega naught, we make a constant of 90, and 10 times less, we have a phase of 0, just like before. Now, there's a little more intuitive way of doing this and maybe understanding what's going on. So, if we look at our model for open loop gain, we have this integrator model. And so, as a designer, what you can do is just set up a triangle of where not to be. I just have to jump out from presentation mode. So I'm just going to take this and drop it right on top of 1 megahertz, the gain bandwidth. Then what I'm going to do is, because it's the integrator model, it goes, as I go to the left, it's going to go up 20 dB per decade. So that's a decade, so I went 20 dB. So it's, again, this is a hand-drawn plot, but I can leave it here, and then I just drag it through here. So no matter what our gain we calculate with R1 and R2, we can't go beyond this spot. And so the simplest way is to calculate the gain and then just draw it straight until we hit this red line. So if the gain were 0 dB, an approximation I could put is this line. I get 0 dB, and then I asymptotically follow the integrator model, right? If I calculated a gain of 20 dB, I could just do that, and it will come here. And yeah, just so you know, omega naught depends on beta, which is the ratio, which is the voltage division of these resistors. As the gain goes up, beta goes down, and omega naught of the amplifier goes down. And so we can see if I want a gain of 100, right, I'll come here on blue, come down red, and that'd be my Bode plot. Now, for the phase where the gain is flat, it's going to be 0 dB. Then you'll have the transition region, right? It'll be minus 45 at omega naught, and then at 10 times omega naught, it'll go to minus 90. So that's really the quickest way to do that. Now what about for the inverting? Well, you can again do this in the nodal method, and it might be better this way. But because you might be a little bit confused when you're trying to use the system approach, because while you can see that there's feedback from here to here, rather than this being ground, you have in. Well, actually we just use superposition. We find what is the contribution at this point due to V out? Well, you just short that and you get R1 divided by the sum of these. And then how do we do the input? Well, you just short V out, which is the voltage division Alright, but I invert it. And the reason why is, and why don't I invert the beta, is because the minus sign is here and I'm adding VNS, so I'm going to subtract it. I could put a minus sign here and get rid of that, but to kind of try to keep it the same look as before, that's why I did that. So we just draw out the equation based on this, and so the difference is we have alpha Vn, whereas before we just had Vn. We go through, calculate all this, and now we have alpha 2 pi gain bandwidth, but notice the cutoff frequency is still the same. So I just redone that. We have an alpha, but the beta is still there. It's still first order low pass. What is the gain at DC? Well, now instead of 1 over beta, we have alpha over beta. Calculate all that through, and we get minus R2 over R1. Now, we go back to our transfer function. This is, what you could call a legal or a valid transfer function, but it doesn't jump out at you what's going on. So just to make a small variable change, if 2 pi gain bandwidth equals omega naught divided by beta, and I substitute that in, I get my omega divided by s plus omega naught, my same low pass transfer function as I had with the inverting, non-inverting, excuse me, but now instead of 1 plus R2 over R1, I get the gain of an inverting. Now, to plot this, I can do almost the same thing. Alright, so that's 20, and then I just draw it backwards. Now, if the gain is 1, it's not really 1 for an inverting, it's minus 1. Alright? But we're taking the magnitude of that, so in fact it's still the same. Now, yeah, for a kind of a first pass, if your gain was, minus 1 or 0 dB, you could draw this. If the gain so you wouldn't really have negative 20 dB of gain in this case. It's really 20 dB of gain with a phase of minus 180, right? And I can keep dragging this up. And I'm going to go into that a little bit more. And so the same thing, the higher the gain, the smaller the cutoff frequency. And so this would look almost the same as the non-inverting, except it would be the phase. And so what we would get here is, and this is the hard part, is you should get minus 180 degrees of phase because the gain is minus 1, right? Or I'm saying the gain is minus, this one down here. So the gain is minus 1, which gives us 0 dB. Almost out to here, and I'll tell you why it's not exactly out to there. So the phase would be from here to here, minus 180. then at omega naught, which is actually a little bit less, I'll get into that why later, then at omega naught it's minus 45, and that 10 times omega naught it goes to minus 180, minus 90, or minus 270. I'll try to show this a little bit better in LT Spice. Okay. So here's everything in LT Spice, and the gain is 6 dB for the inverting, non-inverting, excuse me, and it's 1 for the non-inverting, for the inverting. Now you can see that you have your gain of 6 dB, and then it rolls off at omega naught, and then it actually lines right up on the integrator model. But the gain of the inverting, it's at 0 because R1 equals R2. That gives 6 dB on the non-inverting and 0 dB on the inverting. Now you can see that for the purple line, the phase goes from 0 to minus 90, but that LT Spice has done for the inverting plus 180 down to 90. Well, that's because LT Spice has a choice, right? 180 and minus 180 numerically is the same. Physically they mean different things. And you could manipulate this axis, but it's probably not worth it. So the difference is that you go from 180 down to 90. But really, you can still see it's a 90 degrees difference in the phase shift, and that it's happening, and that, excuse me, and that if I come down to approximately 45, this is omega naught for the non-inverting and the inverting. They're happening at the same place. It's just the gain is higher, so it moves this curve up. And you can download this file and look at it. So when I first did this, it kind of threw me that the gains, it wasn't lining up the way I wanted. And so let's just summarize what's going on. So you have the transfer function of the inverting and the non-inverting. Okay, so let's just calculate some out. So you have keep R1 1K and then vary R2 from 1, 10, 100, 1000. And so if we look at beta, we get something almost to 1, and then it gets smaller. Alpha is the voltage division the other way, and it starts off small and gets bigger. So the gain of the inverting op amp is just this times that, this divided by that, taking the times minus 1. So it starts off less than 1, right? And look at where it hits minus 1 or 0 dB. Look at omega naught. It's a little bit above. That can't be right. I apologize. Oh, sorry, bad day. Of course it can be bigger because omega naught is bigger than I'm sorry, I was just this is omega naught, not the frequency term, so it is bigger than 1 megahertz. I was just checking my work, and I'm running out of time, so I can't really go back and edit this video. But look, for 1, a gain of -1, omega naught is a little bit over 3 megaradians per second. If you want to put that back to frequency, just divide it by 2 pi. But look at the gain of the non-inverting where it hits 1, right? Omega naught is twice as big, so that's why they don't line up. And so yeah, it kind of looks like if you want to extend your frequency, try to use a non-inverting. But what happens is when the gains get really big, it almost doesn't make a difference. So let's just I'll make R2 100K, you know, a very large number, and then we run it, and notice, because minus R2 over R1, you know, 20 log of that is almost the same as that plus 1, and you can see that the curves line up. That's why when we go back here, yep, even though in reality we're getting this, right, at higher frequencies, we're getting this. And so I tend just to draw it like this, where, you know, you'd have 20, 40, 60. I hope that helps.